In the last video, we already saw the definition for the state transition matrix. Let us revise it once again before moving on to study the properties of state transition matrix. The state transition matrix is represented by phi of t, which is also known as e raised to at, and the formula to calculate it is Laplace inverse of Si minus A inverse. Let us see the properties of state transition matrix. Now, the first property is phi of 0 is equal to I. The value of t here is to be substituted as 0. So phi of 0 will become e raised to a0. Anything multiplied by 0 is 0, so it is equal to e raised to 0. Anything raised to 0, answer is 1. But now we know that as it is a state transition matrix, the number 1 in case of matrix represents identity matrix. Therefore, phi of 0 is equal to I, that is identity matrix. So remember the very first property, phi of 0 is equal to I. Next, phi of t is equal to phi of minus t inverse, or phi of t inverse is equal to phi of minus t. Phi of t, as we know, is equal to e raised to at. Phi of minus t will become e raised to minus at. Replace t by minus t. As we know, a raised to m bracket raised to n is a raised to m into n. So, we can write e raised to minus at as e raised to at whole raised to minus 1. E raised to at is phi of t. So it will become phi of t whole raised to minus 1. So the second property, phi of minus t is equal to phi of t whole raised to minus 1. Phi of t1 plus t2 is equal to phi of t1 into phi of t2 is equal to phi of t2 into phi of t1. Phi of t1 into phi of t2 is same as phi of t2 into phi of t1, means it obeys the commutative law of matrix multiplication. Now, phi of t1 plus t2 is equal to e raised to a t1 plus t2 is equal to e raised to at1 into e raised to at2. What is e raised to at1? It is phi of t1. And what is e raised to at2? It is phi of t2. Hence proved. So phi of t1 plus t2 is equal to phi of t1 into phi of t2. Fourth property, phi of t whole raised to n is equal to phi of nt. Replace phi of t by e raised to at. Again, the property a raised to m bracket raised to n is equal to a raised to m into n. So at will get multiplied with n. It was equal to e raised to a into n into t. Ignoring a, the term nt is left out. So e raised to a nt will become phi of nt. So the property phi of t whole raised to n is equal to phi of nt. The last property, phi of t2 minus t1 into phi of t1 minus t0 is equal to phi of t2 minus t0. See, in this case, we have to apply the last property. As we know, phi of t2 minus t1, applying the last property, it will become e raised to at2 into e raised to minus at1. Similarly, phi of t1 minus t0 will become e raised to at1 into e raised to minus at0. Phi of t2 minus t1 into phi of t1 minus t0 is equal to, substitute as we have seen the values of phi of t2 minus t1 and phi of t1 minus t0. We can very well see that e raised to minus at1 into e raised to at1 will get cancelled out because they are having same magnitude but they are opposite in sign. So what is left out? E raised to at2 into e raised to minus at0. It will become e raised to a in bracket t2 minus t0. What is this? It will become phi of t2 minus t0. So the last property of state transition matrix is phi of t2 minus t1 into phi of t1 minus t0 is equal to phi of t2 minus t0. The state transition matrix properties are very important because most of the times in university exams the question is asked what is state transition matrix and enlist the properties of state transition matrix. This question will come for 6 marks. You have to write 5 properties which will carry 1 mark each, and you have to write the definition of state transition matrix which will carry 1 mark.